node from a binary tree. So basically, I'll basically start with the most complex case and then I'll look for some simpler cases. So if I talk about the code, there is a helper function which will deal with only deleting the node and then returning the node of the resultant or returning the root of the resultant tree or subtree, whichever it is, depending on the situation. And then there is one particular function which is the parent function of this particular function, which will basically figure out uh, basically search the value in the binary tree and then delegate the function of deleting that value from the binary tree to the helper function. Okay, so I'll come to the code later, and then basically so start off, I'll start with as I told earlier, discussing the difficult cases and then going towards the easier cases or the edge cases. Right here, the edge cases are pretty easy, so it's not an issue. So let me go with the most complex case first. So basically, uh, what we do is that we need to delete this node, right? Suppose if you have to delete this node, or pardon, not this one. Suppose you have to delete this node. This is the node to be deleted. Let it be D, right? And then what we'll do is that we need to find a replacement for this deleted node. And this is a good replacement for this deleted node. Let this right node of this node be null. So this is a good replacement because this right node is null, and basically this entire thing can be shifted here. So if I can take this entire thing and shift it here, you understand, right? So this entire thing can be kind of shifted here, and this null thing would go. Let me delete. So this null will go and this entire thing will be shifted here. It's still a valid binary tree, and then we'll return this node as the new head, this particular node, and then will be sorted, right? uh, I don't know how to select this. Okay, so this will be sorted. So there is the main strategy. You figure out the left node of the initial root, and then figure out the right, go keep going right from that node uh, till we find a node which has a right node whose right itself is null, like in this case which I just showed you, and then shift the right of the root to here. So this deleted node is the basically original node to be deleted, and this is the right of this node. So not this deleted node, but the right of this node has to be put here. So I can probably, sorry, I can delete this, and then this thing has to be put here, right? So this is how the final tree would look like. Let me okay, hope you got the idea, right? And then this is one case. What are the other cases that are possible? If this is null, right? If nothing is there, so if the node is related to be null, then basically we don't need to do anything. So that is one case. And then suppose this is the deleted node and its right node is null, then we just return this node, right? And similarly, if the left node is null, then we just return this node. Okay, so let me draw a binary tree and try to simulate these kind of edge cases. So what would be a simple binary tree? So let me take probably one here and then two here. So and then let me take three here. So suppose this is the node to be deleted, right? So this is the node to be deleted. So what do we do is that we return, since this left node of this node is null, we return this three node and see that the resultant binary tree still is a valid binary tree, right? So if instead of this was a scenario like this was a three node and this was another two node and one node here, and again this two node was the one to be deleted for, but in this case now the right node is null, but still we'll return this node's left node, right? And the resultant tree would be this one, which is a valid binary tree, and we have effectively deleted the two tree. So basically I went through three cases here. One case is okay when it is a normal thing, when none of the left or right nodes of the deleted node is null, and here either the left node is null, in this case the left node of the node to be deleted is null, and this in this case the right node of the node to be deleted is null. In both those cases, we just return the other kind of child, and then we are done, right? So this generally all these computations are taken care by a function called helper, which I'll show in the code. Pardon my handwriting, right? And then okay, so this is the only the deletion part, and then we come to the identification part. There will be another function which will deal with only the identification. Now let us look at the edge cases. Suppose we pass in a value and a root of a tree, right? And in trying to delete and trying to figure out what this value in the is there present in this tree, and then delete this. So one edge case can be the root itself is null. So this is null, right? So if the root itself is null, then what do we do? We do nothing and then return the root or null, whatever you may feel like. Basically, we don't have to do anything and return a null value, right? What happens in the other case? In the other case, let the root itself have the value as null, right? So basically, in the program, this value is not value; it's called key, and the val and the and basically the attribute of the root which stores the value of the root is called val. So this is val. So basically, we're trying to compare the key with the val right here. And then what happens if the root that is passed in itself is the key to be deleted? Then in that case, we don't need to do anything. We just uh, return whatever helper returns. Right? We directly delegate this root to the helper, right? Because helper basically takes in the node which has to be deleted. So we directly pass that through, and then helper will do the rest. And how does helper work? That I've already explained previously, right? And then there are other cases. So these are the simple scenarios. Then what do we do? Then we basically either will go to the left node, left subtree of the root, or we'll go to the right subtree of the root, right? And either we'll immediately find the value in the left subtree or immediately find the value in the right subtree, or we need to keep going forwards. So how do we do that? So I'll just write a very simple pseudocode of how that is done. So basically we'll basically do a while loop. We'll keep looping till the root is not null, right? Root not equal to null. We'll keep looping. Pardon my handwriting. And then what do we do? And then we have so one scenario is so basically the initial check is either the key will be less than the value in the root, or the key will be greater than the value in the root. So if the key is less than the value in the root, we have to go to the left subtree. There also we have two scenarios. Either we immediately get the key, either the left child of the root itself holds the key that we're looking for, or we need to keep moving forwards, right, or downwards. And same for the right subtree, same scenario for the right subtree, just in reverse. Okay, so I'll just solve for the left subtree and then not solve for the right subtree, and then show what are the how we are dealing with figuring out what the key is, and then passing and then calling the helper in the appropriate manner, so I should deal with the deletion, right? So so we only look in the left subtree when the key is less than the right less than the value stored in the root, right? So basically this will only be triggered when key is less than root dot val, right? Then we are talking about something we need to do, right? And the else case will just be the opposite of what we were doing here, so I'll not be discussing that. You can just copy paste whatever is written on the top and just replace left with right, and it will be done, right? So I'll only be solving this case. So now, okay, so the key is less than root. So what can happen? So maybe the left child of the root itself has a val which is equal to the key. So in that case, what will happen? First you need to check if the left child exists. So we'll check that. Probably I should use some text here. I'm just freestyling a bit, so pardon for that. Okay, so what we do is that either root dot left should not be equal to null. You just have to make sure, because we're going to access something of the left. So this is just a sanity check kind of. And the root dot left dot val should be equal to the key that you're looking for, right? So that means the root of the left root is the one which has to be deleted. So what do we do is that we'll basically call the helper here. So we'll call helper here. We'll just and then helper will do everything and then return the resultant tree, and then we'll store it in the root dot left. So now the new root dot left will be uh, whatever the helper returns after deleting the root dot left node. ठीक है, root dot left. मैं पूरा लिख नहीं रहा हूँ, समझ जाओ. Understand, I'm just not writing that this is left, basically root dot left, right? Or if this is not true, if the left itself doesn't have the key, then what do we need to do? Then we basically move just basically we need to continue with this while loop, right? So we need to reset root to root dot left, because we need to reset our search to I mean we need to continue our search in the left subtree. So root will be become to root dot left, and the same thing we'll do in the basically the else loop. It just replace left by right and will be done as I mentioned earlier. So okay, with this I told you how to basically figure out where the key is, and then uh, delegate the responsibility of deleting the key node to the helper function. And here I've explained how the helper function deals with deletion of the key node. It has got three cases. Two are very simple. One is the normal case, and all the cases I've explained, right? And then there is another function. There is another small thing. So there is another function in which we look for this node, right? If you see for the first case, so we need to look for this node, this right node, which is kind of, so the rightmost node of the left node. This is the root. This is the left node of the root. This is the rightmost node of the yellow, such that its right is null. So there is another function to look for it. Basically, what we do is that we keep moving to the right till we find that till we go to a root whose right is null. Right? There is another small function to deal with it. It's a recursive function. It's pretty easy to understand what's happening there. And that function is used by the helper function to figure out this node, right? So okay, now I've explained everything. Now let us go to the code and then just tell you where uh, whatever things I've explained now are present in the code. So this is the first function which is called. This function is responsible for figuring out the key and delegating the task of deletion of the uh, node which has the key, and returning the resultant tree or subtree, right, after deletion. So again, if let us look at simple cases. The root is null, then we don't do anything. Just return null, and the root itself has the value. We just delegate this root to be deleted to the helper, right? And then we store this root for future use, because we need to return this root. If because what we will be doing in this while loop is we'll basically go traverse the tree and go through every portion of the tree, and probably in some sub portion we'll figure out that we'll figure out the key exists, and then we have to modify the sub portion. Then in that case we need to return the original root. So we store that root initially here in this variable, which is returned at the end, right? Now we are trying to figure out what the key is. So obviously, as I mentioned earlier, the case in which the key itself, the root itself has a value equal to key, that already I've dealt with here. And the cases are remaining it. What if the key is not equal to the root well? Either it can be lesser or it can be greater. The greater thing is just opposite of the lesser thing. You just replace left by right and it will be done. And for the when the key value is lesser than root value, either the child node left child of this root, that is root dot left itself, is the value which needs to be deleted. In that case, we basically pass that subtree to the helper to process it, process the deletion step, and then basically whatever resultant subtree is formed, that is basically in the new left root dot left, right? And then we break, because we don't need to do anything else. You need to get out of the while loop and then return the original root. So that's why we break here prematurely, or we should and if it is not this in the case that the immediate left child is doesn't have a value equal to key, then we need to basically keep probing the left subtree, and then basically reset the root to the uh, left child of the root, right? Same thing we do the right case. And then let's look at the helper function now. So helper, what does it do? Obviously, if the node right is null, we return node left is null, return the node right, as I already have explained. And then if it is not the so, then we have the normal case in which we figure out this node, right? This kind of node using passing using this function called find last, right? I'll be oh look, let's go into this and see what it does. So basically once a node is passed into this right, it will basically keep on going right till we get to a node which has which has right equal to null. So that is what it does. It is pretty simple, evident from looking at this small 2 3 lines of code of how that is done recursively, right? And then that, so again we are back at this line. We basically get that particular right node, extreme right node, starting from the node left, and then store it in this variable. And then that the right of that is null. So instead of null, we'll be setting it to the node right, and that will be our new binary tree. That is the change that is required for formation of the modified binary tree after deletion of the root node here, or the node here. The node will be deleted is node in this case, right? And then that's it. And then we have to return the node dot left, because the root is deleted, and the root dot right or node is deleted and the node dot right is shifted somewhere else. So now the new root of this root of this subtree, which had originally the root of node, is node dot left, and that will return now, right? So that's how the helper works, that's how find last works, and that's now this whole delete node uh, function works. And I've explained now everything. Hope you understood the problem. This is a little bit complex, and probably you need to think about this a bit. But I'm pretty sure that once you go through this and think about this for probably 15 minutes, you'll be able to understand what is exactly going on and how everything comes together. Right. So with that, I'll see you in the next video. Thank you. Bye.